Okay, so let us start. Welcome to week 8 of this interactive session. Myself, Abhimanyu Pratap Singh. I am a research scholar at IIT Delhi. So today, first we will be going through some of the lectures that professor has uploaded on the NPTEL website. We will be looking through those examples and some other examples as well. I will show you what step ODEs are, how they and what solvers are available in MATLAB to solve them. And furthermore, then we will look at the MATLAB's event function, which can be used to detect an event, and we can then use that to stop the simulation or to do some other stuff with the simulation. We can check some of the conditions that if we want to check, and then based on those conditions we can do other stuffs. Okay, so let us begin. Yeah, so let us first discuss how do we convert an ODE or ordinary differential equations to a state space form, or how do we convert an higher order equations, higher order ODEs to simpler first order equations, because as we know ODE 4.5 is a first order solver. So we need to convert our higher order ODEs, higher order single ODEs into a number of first order ODEs. So let us first see how do we do that. Suppose we will begin with this example. So we all know that it's a second order ODE. Yeah. So we know that it's a second order ODE. We have a mx double dot cx dot plus kx. So it's a spring mass damper. Now to convert this to a first order ODE, since this is like we have x, the variables that we want to calculate, those are x and x dot. So we have two variables that we want to know the time series data for, and so this ODE can be converted into two first order ODEs. So the simplest way to do it is that we want x and x dot, so we will take x dot as one variable and x double dot as one variable. So this is our x vector, x dot vector. Okay, and likewise, yeah. So what I am basically trying to do, I am trying to convert this equation into form of x dot is equal to ax plus some other function, if we have some other function, which in this case is 0. So this will just go to 0. No, why I'm trying to do this is because once we convert this into such equation, then this x is a vector over here. It's not a scalar. So x, this basically is my x. Okay. So I can get two first order ODEs from this second order ODE. I can get two first order ODEs. Fine. Uh, so if I take this equation and I take my x dot as one variable v, then my x double dot becomes v dot. Fine. And similarly x double dot becomes minus c x dot minus kx divided by m. Okay, so we can just use these two equations to write this matrix, to complete this matrix. Okay, uh, I know from this equation that x dot is equal to x. That means x dot is equal to v. But here we don't have a v. We are just writing it in terms of x only. Okay, so this is basically just so uh, so this will be like 0, 1. because if I open this matrix, then I will be getting x dot is equal to x dot. Okay, so this is just identity, right? So that is why I'm getting I'm entering 0 and 1. Now when I write for x double dot, so from this we know that x double dot is minus c by m x dot minus k by m x. Fine. So I can write this k by m over here minus k by m, and this goes over here minus c by m. Okay, so if I open this now, yeah, so now this becomes my a matrix. Fine. If I open this matrix, then I will get x dot is equal to x, and this will similarly becomes x double dot is equal to minus k by m x minus c by m x dot. So I get back to this equation. Fine. So so basically we have converted this second order ODE to two first order ODEs. Okay. Um, any doubt in this? How we convert this first order to second order OD, second order to first order ODs? We will look at some more examples as we go on. So this is the simplest and most popular textbook example. Yeah, so we will look at, we will go to MATLAB and try to solve this using ODE 45. I think I need to share screen from this. Yeah. Yeah, I think my screen is visible. So I should open PPT over here also. So let me just open presentation here also. Yeah. So I already have a function built in for this. But for this, I will just create one other, or I should just use this one. It's fine. If you have any doubt anywhere in between, just ask. Okay. So we have given C as 5 and K as 15. Yeah, so the equation is this is like my velocity. The function is spring damper. I am taking as in the two inputs to this function is time and a vector y, and output is dy, or the time derivatives. Fine. So these are my parameters, and the equation, the first one is I am like my x dot is equal to, if I go back to the, I think there is no right hand. Uh, Let me try to. Yeah, so my first equation is x dot is equal to basically x dot itself, right? Which in this case is the second one. Okay, so like I am, my x vector is like the first variable, the first is x and the second is x dot. Right? And the A matrix we just saw, so the first term was 0, and then yeah, so the first term was 0, and then the second term was 1, and here it was minus k by k by m, and this was minus c by m. Okay, and yeah, and this was x dot and x double dot, right? So we will get, so this is just that only 0 1 x x dot. So I will be getting x dot is equal to x dot. So my y is like this is basically my y. Okay, so dy11 is y2 comma 1, dy2 comma 1 is minus c by m x2. Okay, I will yeah, so minus c by m x dot, so this part, and minus k by m x, so that is this part, and I'm dividing this whole by n. Okay, so any doubt in this? This is just simple. I've converted this equation to a matrix form, and then I am just written that matrix over here. Okay, uh, yeah, so now I will just yeah, so this function is clear to everyone, I suppose. So we will try to integrate this. First, we will set some options for OD. Set rel tall 6 and abstall minus 6. So OD45 outputs two things: time series, time values, and the time series data. Okay, so that should be t comma y OD45. We need to input the function handle t comma y. The function name is spring damper t comma y. Then time. We need to input time values. So I will just input 0 to something like 10 seconds. Then the next one is the initial condition. Okay. So the initial condition given to us is x0 is x. Matlab we can take some constant over here, and the velocity is 0, right? So velocity is my second term in the vector, and the position is the first one. So I will input some, suppose, okay, 1, and velocity as 0. Then the last one is the options, which in this case is just the tolerances. Okay, and this should give me the, yeah. So I got 217 time values and 217 cross 2 as y. So the first one is position, the second one is velocity. Now if I try to plot this, sorry, my laptop is a little slow. Yeah, so this is the position, and similarly if we, this is the velocity. If we decrease the damping a little bit, then oh, sorry, options, I had cleared everything. Yeah, so now we get an oscillating solution. Okay, So a higher value of damping means that the solution decays very rapidly, and a small value of damping means that we get oscillatory solutions. Uh, okay, so now let us. So this is clear to everyone, the spring mass damper. And then I will move to the next slide. Yeah. So we saw over here that yeah, we saw over here that as we decrease this C value, the time series, the time taken by the solver was the time steps. If I increase this to like 10, and then I run this thing again, I get 781 time steps. And if I decrease this to 0.1, same. Yeah, so probably it's trying to meet the tolerances. Let us just remove that part. Yeah, so now for small damping values, it is only taking 221 steps. Okay. If I make it even smaller, it's still taking 221 steps. So I increase the damping value. It is now taking 149 steps. But yeah, but we can see that the solution decays very rapidly. Okay. For the same problem, if I take a very large C value, a very large K value, and a very large C value, okay, and I try to solve it now. Same for 10 seconds. So it is taking 149 steps. I run it for long enough time. It's taking 1041 time steps. Okay. If I increase it even more, so I'm trying to solve for same time, 100 seconds only. But in this case, it is taking around 12 lakh time steps, right? So why is this happening? Now basically what has happened is our system has become from a normal system to a step system. Why is that happened is because if we look at, okay, let me go back to my iPad. We'll share the screen. We'll stop sharing from here. Yeah, so what has happened is my system was x double dot 0 1 minus c by m minus, sorry, this is minus k by m, c by m x dot. Fine. For the given values, this matrix is like 0, 1, minus 10,001, and this is minus 10,000. Right? This is like x dot is equal to ax. Now, if I from basic calculus, suppose if I try to convert this, solve this from using basic calculus. So this is basically dx by dt is equal to ax, and the solution for this is x is equal to e to the power at plus some other terms plus a constant, right? So this is the solution to this part, right? This is clear, right? So if I take some real values of it, then I should be like this is if I calculate the eigenvalues of this matrix A, so I will be getting I can represent this like A matrix A times lambda is sorry, diagonalization of this. So AB is AB is lambda mu, right? Where this is the eigenvalue of this matrix A, and V is the eigenvector, right? So I can write this x as to the power lambda t times some constant k1 plus e to the power lambda 2t times some constant k2 plus a constant or some other functions, right? Mm, Just clear this a little bit. Yeah. So my x has become lambda 1t. Okay. These are basically my transients, and then there should be there would be a particular integral, right? Something which in this case would be zero only. Yeah, but anyways, so now I have two transients, exponential of lambda 1t and lambda 2t. Now, if both of these eigenvalues are real and negative, right, then that means my transients decay very rapidly, and the solution is stable, right? But and if if the eigenvalues are complex number, then there is some oscillatory behavior, and eventually it decays. If the real part is negative only, right? But if the eigenvalues are positive, then my solution diverges. Okay. Now the issue is, suppose lambda 1 is very big, greater than lambda 2. Okay. Then what happens is that my and I am also assuming that both lambda 1 and lambda 2 are real and negative. Okay. In this case, what happens is that my lambda 1 decays at a very high rate as compared to my e to the power lambda 2 term. So basically this term decays very rapidly as compared to this term. So we have like slow time scales in the system. Uh, one of the term is very rapidly decaying, while the other term is slow to decay, or the time scale for that other term is very slow. In in such situations, what happens that ODE45 tries to maintain the time scales, tries to maintain the time scales of the slower part, right? Suppose I have some term which goes like this, and then there is another part that goes like this. right? So now the OD for what OD the problem is that OD45 we try to maintain the error boundaries or error tolerances for this faster time scale, right? Because the transients this transient is decaying very rapidly as compared to this. So what will happen is that for this we need very small time steps, but for the same time step the other term the other this part, there is not a lot of change in that. So for that we could have taken some larger time steps, but since it's a constant, like the time step remains constant, so it does not remain constant, but like the adaptive part is the adaptive thing is very slow as compared to some other solvers. So we will get a very large amount of time steps to solve this problem. Okay, that basically means that our system is very stiff. So we have three like if we have three conditions for the ODs to be stiff. If any one of these three conditions are satisfied, that means that our system is stiff. So what is the first condition? The first condition states that uh, a linear constant coefficient system is stiff if all of its eigenvalues have negative real part and the stiffness ratio is very large. So I already told you. So we convert the system into x dot is equal to ax. Then we calculate the eigenvalues of this A matrix, and if the both the eigenvalues are negative, and then we calculate the ratio of the eigenvalues. This is since a second order system, so we get two eigenvalues and we calculate the ratio of those two eigenvalues, lambda 1 divided by lambda 2. And if this is a very large number, then that means that one of the variables or one of the time series is very rapidly decaying while the other is slow to decay. So that makes our overall system a stiff system. Okay. The second condition is that if stiffness occurs when the stability requirements rather than those of accuracy constrain the step length. Okay. So we saw in the previous lecture that for the Euler's method we needed the h value to be smaller, right? If we take very high h values, then the problem was that the system was uh, diverging, right? We saw one example like that. When we took h value of 0.25 or 0.1, we took a value of close to 1, right? Then we saw that the system was diverging. But if we take by our h values very small, then we saw the system was converging. So what happens is that sometimes the system is such that we need to take very small h values, right? So when we take very small h values, the for the same time from 0 to t, if the h value is very small, then the number of time steps between this 0 to t, those become very large. So the solver takes a long time to solve the same problem. That also makes our system stiff. Okay. And the third one is that stiffness occurs when the some components of the solution decay much more rapidly than others. So basically, this is same as this condition, but yeah, sometimes we don't even have to calculate the eigenvalues. We can simply uh, solve the system for some small amount of time, and we can see, okay, that one of the time series is very rapidly decaying as compared to other time series. So probably the system is just we need to use some other ODE solver rather than ODE45. Okay. Yeah. So is this clear? Fine. Yeah, so let us look at some example. Yeah, so this is the previous one only. So this is the true solution for that problem, spring damper problem. If we take C as 1001 and K as 1000, then we can get the true solution as this value. In here we can see that one the eigenvalues of this A matrix. I will show it. Go back and forth between MATLAB and this. Share this screen. Yeah. So for this, our A matrix is 0, 1, minus C by, no, what would it be? Minus K by M, right? So minus 1000, and the other term is minus C by M. So minus 1001. Fine. If I calculate the eigenvalues of this matrix, so one of the eigenvalue is -1 and the other one is minus 1000. So the stiffness ratio is very high, like it's 1000. Okay. Uh, yeah, so we can get a true solution as this. Yeah, so we get a true solution as this. In this, you can see that this term, this will be very fast to decay, whereas this term, it will decay very slowly, right? Similarly, if we see this, so this, and I plot. So, and on the same plot, if I plot the second one, yeah. So this goes, yeah, so this goes from 0 to a very high value of to -3 in just 0.2 seconds, and then it again decays to 0. So that the transients over here are very large, right? Whereas this, it just directly goes from 0 to, like, this is a normal how it is supposed to be, right? So that is why this OD 458 is taking 1,20,000 time steps to do this. Okay. If I do the same thing, so there is OD 15S in MATLAB, which is a step solver. If I do the same thing using OD 15S, yeah, so you see the same problem is solved in 109 time steps. If I plot the same thing, so we get the same result. Both the plots are overlapping one another, but we get the same result in very small number of time steps. The program also runs very fast, right? If I look at that time duration between this, yeah, so it is like, yeah, initially it's in the range of 10 to the power -7. Okay, then it increases again to 10 to the power 5 -5, then 10 to the power -3, and this is now the increment of 0.5. Eventually the increment is very large, very large, right? So later part, once the transients have died out, it's only the steady state. So the time stepping is like 2 seconds, 4 seconds. Eventually it is like 5 seconds, 10 seconds, 10 seconds, 10 seconds, right? On the same hand, do the same thing using ODE 45. So the time stepping is, if I look at the max of, we'll take this time series from the 1 to n minus 1 and subtract it 2 to n. Yeah, so the maximum is like 10 to the power minus 1.6 into 10 to the power minus 8. That is the maximum time step which is which the system has taken. One to end and T2 to end. Sorry, I think I should have taken the absolute of this. Yeah, so this is the maximum time stepping which it is doing 0.0011. Okay, so in the scale of 10 to the power minus 3, right? On the same hand, if we look at OD for 15s and we calculate the same thing, the maximum time stepping that it is doing is of the order 10. Okay, for the same problem with same initial conditions, same time limits and same conditions, we are getting uh, the different scales of the time stepping that the solver is internally doing. Okay, but we are getting the same solution. So it does not matter much in this example, but there are other systems where it takes a lot of time to solve the problem using OD45 because of that this time stepping. But if we use some step solvers, uh, so if I Google it, there are number of higher order solvers available in MATLAB, not just OD15s. Lab step OD solvers. So MATLAB has what happened? Yeah, so MATLAB has these four step solvers: OD15s, OD23s, OD23T, OD23TV. Each one has its own characteristics, so you can look it up. Uh, like if I check OD15s, uh, yeah, so they also give references at the end that mm, which from which paper the solver is designed. Okay, so you can go through it if you want. Similarly, there is OD23s. So this is a low order method. This is based on modified Rosenbach formula of order 2 because it's a single step solver. It may be more efficient than OD15s. Uh, yeah, but the accuracy is not that much of OD23s. There are very good OD solver. Yeah, let me just. Let me just open this here. So you can see OD45, the order of accuracy is medium, the stiffness, it's a non-step solver. The algorithm is Range-Kutta. OD23, this is also similar to OD45, but the order of accuracy is low. This OD15S, OD23S, and OD23T, the order of accuracy is lower for them, the OD23, OD23. But they use different algorithms rather than Runge-Kutta methods. They use different NDFs, Rosenbrock and trapezoidal methods. But yeah, based on your problem, you can choose between these different solvers. Okay. So we will look at one more textbook problem, which is this van der Pol oscillator. I already have a code for this. So this is basically a second order system, and similar to what we did over here, we take x dot this x prime as v, and then x double prime becomes v dot, and then we create this same matrix, and we get similar to what we did in this part. We get similar equations over here. So I will go back. Write it over here. So we take x prime. Yeah. So this is like x x double dot. This is x dot. Yeah. So for this, the first x prime, I will be getting 0, 1, x, and x dot. Okay. So this is like basically identity. So 0, 1. That is what I'm writing over here. dy1 is equal to y2, and then x double prime. So I will take this whole equation over there. So I will be getting minus 1. Okay, so the issue is that, yeah, it's a non-linear ODE, right? So it's not a linear ODE, it's a non-linear ODE because I have this x prime and x square multiplied together. So I cannot convert this into this state space form that easily, right? So this is a nonlinear ODE, so I will not get this state space form, but I can still write this as my first one is x prime is equal to v, and then my x double prime would become minus x plus mu 1 minus x square, and then I will, sorry, yeah, you get the idea. 1 minus x square. Okay, if I just write, so my x prime would become minus x plus mu times 1 minus x square, and then since I have taken x prime as v, so it will become v. Okay. So now this is like first order equation only. So that is what I have written over here. Okay. So basically y2 is basically my v, and y1 is basically same as x. Okay. So dy1 basically is x prime, and that is equal to v from this first equation, and v dot is equal to, so this x double dot is my v dot. So this is basically my v dot, and that is equal to minus y1, that is minus x, plus mu1 minus x square into y2, that is v. Okay. And MATLAB, since this is like this is uh, a row vector, so MATLAB expects the output to be a column vector. So I'm just taking a transpose over here. That's it. Yeah. So this is clear.
Yes, sir, it is clear.
Okay. Mm, yeah. So I will just try to solve this similar. Yeah. I only have one parameter, so first I will solve with mu is equal to 1. Change this to wonderful. Rest of the syntax remains the same. The initial condition is 2 comma 0. I will change that, and let me just put for 10 seconds. The rest of the syntax remains the same. We'll plot it. Yeah. So this is the for mu is equal to when the it's like similar to a sinusoidal, but something a skewed sinusoidal wave only, right? Uh, if I increase mu to say 5 and I run it again, same plot, I plot it. So now it has it's still a little bit skewed, but the transients are still there. The time scales are like I am in this fast time. So yeah, this part from here to here it is taking around 4.5 seconds, but from here to here it is completing in 1 second only. But still we have sufficient number of points in between, right? Okay, sorry, I have been using OD15s. And so with OD15s we are solving this in 127 time steps. And if I solve it using OD45, so we are getting 270, approximately close to the double of the time steps, right? But the solution is still similar. So there is some mismatch in this transients part. Yeah. So there is slight mismatch in this because of this time stepping. But otherwise, this is like completely overlapping. Okay. Yeah. Now if I change this mu to 100 and solve the same thing, so it still solves in 217 seconds. But if I so it does not update. Okay, I need to save this. Now I run this again. Yeah. So now for mu is equal to 100, it has taken 3500, close to 3500 time steps. Okay. Now if I plot this, yeah. So in the entire 10-second of duration, I am still, this is pretty much close to a straight line. So I think I need to solve it for longer duration. So let us make this 200. Yes, for 200, it is taking 46,000 time steps. I plot it. So you can see this transient, it is taking 80 seconds, and then I don't have any time in between, right? This is a very fast process. It goes from 0.8 to -2 in just less than zero point 0.1 second itself. Yeah, less than 0.1 second, right? And now if I do the same thing using OD15s, So I can do the same thing in 314 time steps, and still I'm getting the same solution, right? And yeah, so if I just close this plot and do this again, so yeah, so this is using OD45. So I have a lot of points in here. So I have like 46,000 points. I have lot of points in this slow dynamics region. This is where it ends, and then I have a point in here. In between, I don't have any point. Okay, I have one point over here. Uh, this is the one point, but in between, I don't have any other point. Even though OD45 is taking very small time steps, very small value of h. It's taking 46,000 steps, but still I don't have any point in between these transient dynamics, right? If I calculate the maximum value of h, so the maximum time step that it is doing is 0.04. Okay. Now I will try to do the same thing using OD15s. It has taken only 314 time steps, but if I plot it, you can see I'm starting to getting points in this transient region also, right? So this was the I think the last point was close to here for OD45, and then directly here. I did not have any point in between, but with OD15s, uh, I'm getting points in this fast transient region also. Okay, and similarly, if I check the maximum time stepping is 14. The minimum, okay, so I will just check the minimum also. So the minimum time stepping is 4.6 into 10 to the power minus 5. In OD45 case, still the minimum time stepping is this, but this is like the minimum time stepping is smaller than OD15s, but still we don't get a point in between because it does not it does not changes the h value based on the system dynamics, whereas OD15s checks if the transients have died out or what is the current situation, and then based on that it adaptively changes the h value. Okay. So you need to see your problem, what sort of dynamics you have. If you have something, what yeah, so let us look at the spring damp. uh, do I have some problem like that? So in this case, like okay, let us check look at the second one. Plot y2. So this is even worse. We have everything close to zero, and then there is a sudden spike, and then again it goes to zero, right? Yeah. So in this, like you can see, this is pretty much close to zero, and then sudden spike, and then again close to zero. Whereas the other one, there are transients in it, then this, and then again there are some transients. So you can see that the time scales for this is very different, right? So you need to see your problem, what sort of time scales you have, how fast the transients are changing, and then based on that you will choose, you need to choose a solver. Do I need to use OD45 or do I need to use OD15s? Sometimes the problem is that OD45 will give you much more accurate results because it is using a smaller time stepping and everything, but it will take a lot of time. It might get stuck inside some loop because it might not be able to meet the error tolerances. uh, it might not be able to meet the error tolerances even by reducing h to a very small value, right? Then it will be stuck in that loop. But that is not the case with ODE 15s. So you need to look at the problem, what sort of problems you have, and then decide on the solver which you need to take. Okay. Yeah. So this is another example. So let us first solve the sample problem that is there in the assignment, non-graded assignment, and then we will look at them. These are basically the same problems, just a little bit tougher. So just open the Swine portal. So we will look at these problems, and then we will again come back to the PPT. We will look at the event detection function of the OD solvers. Okay. So this is just the spring mass damper problem. We already have a function for it. I will just enter the parameters. Just a minute. Yeah, so I will just enter these parameters. C value, two different values of C. Okay, the first one is for C is equal to 2, and K value is 1.6. So it's over damped system. It's under damped. Okay, fine. It's under damped system. Yeah, this is all that we need to change in that. Spring damper 0 Ty. For the under damped system, please report the displacement at T is equal to 1. Fine. So I will just run it till 1. The initial condition is given to us x0 as 1 and this as minus 0.25. Yeah, right. Uh, okay, so they have also given us a T span. So we will just use that T span 0 to 0.1 to 20 seconds. Fine. And then please report the displacement at T is equal to 1. Find. There is some function named find. Let me just directly check. 0.1 is 11th variable, and the 11th variable is okay. Please report the displacement. So the first one is the displacement, the second one is the velocity, right? So this is the answer for this part. 675. Please report the displacement at t is equal to 5 seconds. So that would be close to 51. Yeah. And minus 0.34. Let's check. Non-zero entries in X. K must be a positive integer but can be of any numeric type. It's equal to 1. Yeah, so it will give us 11. Then we can simply take the 11th variable of the first one. So that is 0.665. And similarly, find t is equal to 5. That would be 51. So we can, or we can just write it over here also. Find t is equal to 5, 150. So minus 3.4. And now we can do it for c is equal to 10. Rest everything remains the same. Save this. Oh, yeah. So we will take y is equal to 1, 1, 8085. They have written 1, 110. Okay, let us just do it for this only at 5. So 0.3972. Okay. I hope this is clear. This is simple. Let us look at the second problem. Chemical reactor. The second order, a second order system A plus 2B goes to C takes place in a reactor. The model is given by this. So okay, so we have 3 first order ODEs with the parameter k is equal to 0.2. The initial conditions are given. Solve the above set of ODEs using ODE 45 and report the following. Okay, so we need to report concentration of A at 1.5 seconds. Anjali, do you have any doubt?
No, sir.
Okay. So yeah, we will write this equations first. Reactor itself 2 comma y and yeah, so dy1. Okay, let me parameter k as 0.2 minus k times. Yeah, so I'm naming my variables as y1 is equal to ca, y2 is equal to cb, and y3 is equal to cc. Yeah, we have ca, cb, cc. Yeah. Okay. So dy1, that is dca by dt, that would be minus k multiplied by ca. So y1 multiplied by cb to the power 0.6. So y sorry y2 to the power 0.6. Yeah, then d by 2 minus 2 times k times y1 times y2 to the power 0.6. Yeah, and then we have dy 3 times y1 multiplied by y2 to the power 0.6. Okay, so none of the reactions are dependent on C concentration of the C. That is the output. Fine. Yeah, so we will just save this. That's it. That's the function. Now t comma y OD45 t comma y y. We need to give the time. I will just give 0, 0, 0 0.1, 0.1 to 10. And then the initial concentrations, that would be 2, 5, 0. Okay. I think it will give me an error. Yeah, so it must return a column vector. So that is what you can do is that you can just write all these variables as a column vector, but then you need to write like 1 comma 1 2 comma 1 and here also 1 comma 1 2 comma 1. Simplest way to is to just write this as that and then take the transpose. So now this will be a column vector, and now if I run this, so it will run fine. Yeah, so we need the concentration of C at 1.5 seconds. So I will just write that only. Find so T at 1.5 and CA, that is the first one only. So this second term will remain one only. That should be the answer. 1.02, 0.0201, and similarly for B. So this should become 2, 3.0403, and for C this should become 3, 799. And then at T was 7.5. So I will just change this to 1 and this as 7.5. Yeah, for this you need to also make sure that the time scale that you have taken. Okay, let me just do this and then I'll 0.1770. So suppose so this will not work fine. T is double equal to 7.5 if I don't have a 7.5 in T vector. So you just need to make sure that when you are giving this time the time span that you are giving over here, it contains all the time where you all the time steps where you want to calculate or where you want to find the concentrations. Okay, that is why I have given 0.1, because that will include all of these times, right? Or I could have taken 0.25 also. That should have also worked. So you just need to make sure that you are giving a interval such that it contains all the time steps that you require. Okay, so that completes the second problem. So this is the third problem. Also two first order ODEs. So we'll just create another function. So my y1 is h and my y2 is t. Okay. I have 4 parameters. So I will first write those values, alpha, beta 0.5, gamma 0.5, and delta is 2. Okay. Now my equations. So dy1 is equal to alpha multiplied by h. So h is my y1, okay, minus beta times y1 y1 times y2 by 2. Yeah, okay. This is gamma times y1 times y2 minus delta times y2. Okay, and this is what this is all I need. We'll save this. Mm, Happened to MATLAB. Save this. So they're asking us to solve using OD15s. Okay. Time span is up to 15, and the initial conditions are, so in this case we have only two initial conditions. First one is 1, the other one is also 1, and we need to remove this. Also we need to convert this into a column vector. Fine. So I will run this. Same thing again. 2.5 is 2.5, 7.8589, 593. And this is same thing with 2. So the first one at t is equal to 10 seconds. 4, and this is same thing with the second variable. 2.4169. If we look at the plot, let's just see what is there. I don't think we will have any problem for this. So let us just do this with E1, Y1, 5. Yeah, so it still works fine with OD45 also. But if we plot it, hold on. Yeah, so plots also overlap. It's not that fast of dynamics, like both the both the time series are more or less same time scales, on the same time scales. So that is why both OD 15s and OD 45 both are taking same number of steps. Yeah. Fine. So the next one, pharma industry example. The model of a pharmaceutical reactor is given by the following equations. Okay, so three first order equations. In the above equation, S is concentration of sugar, X is concentration of biomass, P is concentration of pharmaceutical product. The rate of the reaction is given by this. Okay, the values of various parameters are D, S in yield coefficients. Initially at T is equal to 0, the concentrations are this. Use OD 15s to solve the above system of ODs and obtain the concentrations at fine. Okay. So for every time step, we first need to calculate this R scalar value, and then we need to calculate we need to find these time rates. Okay, so I will do that. So P comma Y. Yeah, so my S is Y1, my X is Y2. If you guys have any doubt in between, just ask. Okay, I know I'm going a little too fast, but this is all like same thing. We are repeating same thing again and again, so that's why I'm doing fast. P is Y3. Yeah. So for every time this y is, it's just a vector, right? It's not a matrix. So first we need to calculate the value of R. S is my y1 multiplied by x, that is my y2, and then I will divide by the summation. Okay, 15 plus S y1 plus 0.2 multiplied by E, that is my y3. Now we go to the equations. Okay, let us also, we need to also have this constants. So D is 2.5, S 5, YX 0.7, YP 0.3. Yeah. So D by 1 D times minus Y1. The other thing also that you can do is that I can just write over here as Y1, X as Y2, and P as Y3. So now probably to change this also, so I can just directly write whatever it's written over, I can just write it over here. Yes, 0.2 times t. So I can write my equations also. Yeah, but here I am outputting dy only, so I will just keep this as or else I can also make this similar to that only. Dp is equal to d times s in minus s minus r just a minute. Dx is equal to minus d times x plus yx times r, and then dp minus dp, sorry, d times p plus y t to r. It's correct. D times s in minus s minus r minus dx plus yx r minus dp plus ypr. Okay. But now since I am outputting dy, so I need to make sure that my output is dy only. So dy is equal to, and it should be a column vector. So I will make this dp dx and sorry, yeah, this is ds dp dx and dp. Okay. Fine. Use this OD15s. I will change the function name. So we need concentrations as at 2.5 and 10. So I will take this time scale as 0.25, go till 10. The initial concentrations are given as 0.5, 0.5, 0.1 and 0. 0.5, 0.1 and 0. Okay. Yeah. So now we need sugar concentration at t is equal to 2.5. Yeah, so it's basically the same problem. Sugar is the first one. So 3.3855. Sorry, 3.3855. And 1 is the biomass. X is the biomass here. 1.1240. Product concentration, third one. So 0.4816. And then product concentration at 10. 7426. Okay. Okay, so something is wrong in this. Test is correct. Is 2.5, Sn is 0. Sn is 5, Yx is 0.7, Yp is 0.3. Okay. It's the equation wrong. D times Sn minus s minus r minus dx plus yx into r. R is 25 times Sx 15 plus S plus 0.2 times P. This is correct. D times Sn minus S minus R minus dx plus yxr minus dp plus ypr. This is correct. So not 15 should not 15 25 into x. Yeah, okay. Yeah, I gave the initial condition wrong. So this is like 5, not 0.5. I gave it 0.5. Fine. Yeah, now this should be correct. 2.7716. So you need to check your initial conditions properly. 601 and then the third one 6685. Finally the fourth one. Yeah, so this is correct. If I entered a minus sign by mistake, this should not be minus. Concentration can never be negative. Entered a minus sign by mistake. Fine. So any doubt in any of this problem? Any doubt in any problem of the graded assignment? Like you are not able to understand anything or like that? These are like similar problems. Not take you more than 20 minutes to solve all of them. So now let us look at some other things that I wanted to tell you. So these are basically the similar problems, like problems in ODs, first order, two ODs in first order, like that. So you can solve them easily. So this is a second order ODE, nonlinear ODE. You need to convert it into first order ODE forms, and then you need to solve them. Yeah, and this is a third order ODE. So I will try to solve this third order ODE for you. Back to this. So this one I will just show you and then you can solve the rest. So we have z double dot z triple dot plus z double dot minus sine z is equal to t. Yeah, so like a first order case, I will take z dot as v and z double dot as uh, w. Okay. Yeah, that should work fine. So now I can write. You can see that I don't have any z dot. I don't have any z dot term in here. I will directly go to z double dot. So that z double dot is w. That is fine. Z triple dot is t plus sine of z minus z double dot. So that would be t minus sine of z minus w. Okay. And this z triple dot, that would be my w dot. Okay. Because if I look at this, then z double dot is my w. So my z triple dot would become my zw dot. Fine. Similarly, from here, z double dot would become v dot. Okay. And that would become my w. So this is, yeah. So this is like my one equation. This is one equation and this is one equation. Okay. So if I combine all of them together, so one equation I will get is simply of yeah, if I try to create a function, then like it's like dy is equal to something and t comma y, right? So some function name and t comma y. So my dy1, that would be, this is my dy1, right? Z dot. So that would be my y1, dy2. Dy2 is my z double dot. That is my w. So basically that is my y2. And then I have 3 z triple dot, right? So that is my this term. Okay. T minus sine of z is my y1 only. So sine of y1 minus w, that is y3. Okay. Yeah, let me just cross check. So z double dot z dot is equal to v. That is fine. Can write it as, yeah, sorry. Z y2, that is this part. That should be y3. Fine. So what I have done is my y vector is basically z, w, and b. Okay. So I have three unknowns, and my y dot is, or dy, my dy by dt is z dot, sorry, zvw, and this is z dot v dot w dot. Fine. So I write my z dot as from this equation as v, right? So that becomes my y2. Okay. Similarly, I write v dot as w from this equation. So that becomes my y3. And now the last equation is so my last equation is w dot, right? So this is my w dot, right? And that is t plus sine of y1, like it's sine of z, z is y1 minus z double dot. My z double dot is w, so minus w or y3, because my w is y3, right? So is this clear to everyone? How do we convert a third order ODE to a first order first order ODEs? Fine then. Uh, yeah, so now you just need to write a function with all these three first order ODEs, and rest is simple. OD45. Given the initial conditions are given to you, you can simply solve this. Fine. So this is clear to everyone, right? You can, any one of you can speak. Yeah. So now the next part that I wanted to tell you is the detecting events part. So OD45. So OD45 has this event detection functionality where I can pass on as this OD option. So we have these OD set, right? If I type OD set. So I have all these options in OD set. One of these options is the event option. Yeah, so events function. So it can help us locate certain events within the integration scheme. So event functions can help us detect when certain events occur during the solution of an ODE. Suppose we want to calculate when does the ODE, like when does one of the variable cross zero, right? Suppose I drop a ball from some height, certain height, and I want to know when the ball touches the ground. So the simplest way is that you let the solution run for like a long time, and then you check when the height variable cross the zero crossing, right? When did it become negative first, and then that is the time when it reached the ground. But you need to run the entire scheme, like you need to run the simulation for a very long duration for it to reach the ground and then cross the ground plane to reach the negative z or negative y plane, however you see that, and then you need to manually check it. The other way is to use the event function of this OD solver. And so event functions takes an expression, which in this case would be the height, and can help you detect an event when the expression is equal to a zero. And they can also signal the OD solver to halt the integration when they detect an event. So you can tell the OD45 or OD15s, any OD solver, to stop the integration or to stop the simulation when that event function is triggered. Okay, so that helps us, like, suppose you have some chemical reaction simulation running, and you want the simulation to stop when a certain reaction, or when a certain chemical concentration reaches a certain value, right? Thus, some of these chemical simulations, they take a long time to run, and so you want them to stop for a certain value of concentration. So you can't let them run for a long time, right? So you can use the event function for that thing. Okay, so we'll look at few examples using this event function, and then we will call it a uh, yeah. So the first one is the bouncing ball example only. So I think we don't have okay. I think I made a script for that example. Yeah. So this is the function. This is my function definition of these two equations. So y dot is equal to v. This is the equation for the height, or this is the equation for the depth of the ball, and this is the velocity of the ball. Right. So this is what it is over here. dy1 is equal to y2. So y1 is equal to height, and y2 is equal to velocity. It's also written over here, right? So I just need to integrate the velocity to get the height. So that is why dy1 is equal to y2, and my acceleration is g only, right? So minus 9.81. So that is what dy2 is, minus 9.81, and I need to convert into a column vector. So that is this transpose. Another event function is yeah, it takes as input the same t and y, time and the vector y. You can name it anything you want. I just name it events. The output are three things: the value, is terminal, and direction. Okay. Uh, yeah. So value y1. Yeah, this value is whatever condition you want to give. Uh, I can give any condition I want. It need not be a simple term, simple one term. It can be a complex expression. You can do a lot of things inside, and whatever the final expression that you want to check for zero crossing, you just need to enter that over here in the value field. Okay. Is terminal is that if you want to stop the integration, then it should be 1, otherwise it needs to be a 0. Okay. So it's like the OD45 will check for all these three values only. So the value it will check, okay, is this expression 0? Okay, fine, it is 0. Then it will check is terminal, what is the what do the user wants me to do when the value reaches 0. Okay, so if is terminal 1, that means that you need to stop the integration. So OD45 will exit the integration or stop the integration. And the third one is the direction. So like I have something like this, right? So this is my number line, this is my 0. So I can cross this 0 either from this direction, or I can cross this 0 from this direction, right? So we just need to mention from which direction we want to cross this 0. So in this case, it is from the negative direction, because we are coming from top. In certain cases, it is the positive direction. It's the negative direction because it's like my 0 is over here, right? And the ball is coming from top. So it is like this direction, right? So this is the negative direction because we are going in the negative axis, right? If you are coming like this from top to bottom, or you are going from the negative axis to the positive axis, then this direction would be by plus one. And if you don't need to check the direction, you just want it to cross zero, then you just need to enter a zero over here. Fine. Is this clear to everyone? This event function. If you have any doubt, you can ask. Fine. So yeah. So now in the options OD set, I will make this event field. So we have this events field in OD set. I will make this. I will pass on the function handle to the my event this event function to this events field, and the rest is simple. Okay. This OD45. This is just my function handle. Uh, this is my function handle. This is my time scale. Whatever time t span I want to give. The third one is my initial condition, and the last one is my options. Okay. Fine. Now the output, if in case I'm using the event function, the output, like I can just write ty, that is also fine. But I get three additional outputs out of them. Okay. So the first one is the time step, at which time step the event is happening. What is the value of y at that time step, and what is the number of that time step, like what's the instance. So if it's like not terminal is set to zero, that means it will just count that. Okay, this is the okay, the event has happened once, and now the integration is continuing. Again zero crossing happens, it will again count that. So I how many times the zero crossing is happening, that I can get as output in IE. Okay. One other thing is that these values, they need not be a single value. All of this value is terminal direction. They can be a vectors. Suppose I have multiple, I have, suppose, okay. In this case, like I have two variables, right? Y1 and Y2. So I can put two different conditions for Y1 and Y2. In that case, like value one, I can just write it as a vector. Okay. So I can make this value one and give one condition for something. And similarly, I need to have this, and I need to have direction. Okay. So the number of these expressions you have, for each expression you need to have its terminal condition, and you need to have a direction. Okay. If you have three number of conditions to be checked, then you need 3 cross 1 is terminal vector and 3 cross 1 direction vector. Okay. Fine. So yeah, so I just want to check when my height crosses 0. That means I just want to check when my y1, that is the first variable, it becomes 0. Okay, or when it crosses 0, and I want my integration to stop at that instant, and I want the direction to be negative. So that means I want the 0 to come from top. Okay, because it's like the ball is dropping. That is why my direction is -1. I am going from positive axis to negative axis. Okay. Yeah. So you see, I'm running the simulation for a long time, so I'm running it for 30 seconds. I am dropping. Yeah. So I'm dropping the ball from a height of 20 meters and a zero velocity. Okay, fine. So it has run. So this is the height of the ball. So you can see I have given my t final as 30 seconds, but still the simulation only ran for close to 2.2 seconds, close to 2 seconds. At 2 seconds, my ball touched, like my edge or the first variable crossed a zero crossing, so the simulation is stopped. I got the output as 2 seconds. Okay, so if I check this t, so that t is 2.019, and my ye, that is where crossed the zero crossing. So that is like, this is the first one, the displacement, that is minus 1.12, and the velocity at that instant is minus 19, that is 19.8 in the downward direction. Okay. Fine. So is this clear to everyone? The event function. Any doubt you can ask. Fine. So okay. So I can use this event function to get some very nice graphs also. Uh, like in this case, even if I drop the ball from a height of 20 meters with zero velocity, it is bound to happen that the ball will touch the ground, and then it will again bounce up, and then again touch the ground, and then again bounce up, then again touch the ground. It is not like it's not a one go process only, right? The ball will bounce again and again. So if we want to do that using this OD45 only, then what do we need to do is that after every drop, we need to change this initial condition, right? And we need to get, and once the ball again touches the ground, we again need to restart OD45 with a different initial condition, right? What this initial condition will change? What will change in this initial condition? My displacement would remain zero after every drop. Like this is my first drop. Now, once it has touched the ground, my initial condition would be y1 would be zero, and y2 would be the velocity in this direction, right? A positive velocity. So I need to change my initial conditions after every instance of the ball touching the ground. So how do I do that? Suppose I want this to do what happened. I want this to happen for 10 drops. Like I want to calculate 10 bounces. Fine. So I will start from the same initial condition, 20, 0. This is the first initial condition, dropping the ball from height of 20 meters. Then this is just empty vectors. And this is one instance, the first instance of this happening. So at the first instance, my y0 is this only. So the ball will be dropped from a height of 20 meter. Now, once that has happened, the event function is triggered and the simulation is stopped, right? So after that, I will check the length of my t vector. Then out of that, I will take the t vector from that instant to from the second instant, because the first instant has already happened, right? For the next time step, it will be so the for the next time step, okay, like the ball has dropped. Now for the next motion of the ball to go up, this time step at this point and the time step at this point will be same, right? So that is why I'm taking all the t from the second time step to the nth time step. Similarly, I'm all taking all the y values from the second time step to the nth time step. I'm not taking the first one, the first element of this vector, because that is already included in the previous y, right? Yeah, so I'm taking only the height in this part, and this is every time when the ball is touching the ground, and this is the height when the ball is touching the ground. Now what I'm doing after every drop of the ball is that I'm changing this initial condition. So I'm changing the first vector to 0, that is the height to be 0, and I'm changing my velocity to be with whatever velocity the ball touched the ground. I am taking 0.9 times of that velocity, and I am just inputting that as my next initial condition. Okay, and I'm taking a negation of that because the velocity will be in the upward direction for the further upward motion, right? Okay, and my t start is then t, which is the time step when the last like it is the time step when the ball last touched the ground, and then I'm running it for 30 seconds after that. But it will not run for 30 seconds. It will stop in between as when the ball touches the ground again. Okay. And then I'm plotting it. Any doubt what I'm doing over here and why I'm doing? No doubt? Okay. This is just the conservation of momentum. Okay. Yeah. So I will run this. So you see, this is for 10 bounces of the ball. I'm starting from 0. This is my first bounce. Then after first bounce, I am changing the initial velocity to 0.9 times of whatever the velocity was at this point. That is the velocity for second bounce. And then once again, when it comes back, I am again changing the velocity, and yeah, this continues. Okay. Fine. Uh, if I see my TE out, yeah. So this is like all the time steps when the ball touched the ground. The first is at 2 seconds. Then the next one is happening at 5.65 seconds, then 8.92 seconds, then 11.86 seconds, like that. Okay. If I try to store instead of this, if I try to store the velocity of the ball, I'll run this again. Okay. Sorry, this should be one only. Here I will store by 2. Oh, sorry. Here I will store the nth term, second one. So I'm instead of storing the position, I am storing the velocity. Okay. This. So I will get my y out. Yeah. So this is my velocity after every bounce. Okay. After first bounce, it's minus 19.8, then minus 17.8, then 16, minus 16, minus 14, minus 20, like that. Okay. Yeah. So this is the event function. We can use the similar function to get this, the Mahendra Singh Dhoni example that professor showed us in the video lecture. So the question was, if the velocity is if the boundary is at a distance of 75 meter, will he score a 6? So you just need to check when this y value is becoming 0. Okay, so for the time step when the y value is becoming 0, is x greater than 75 or not? If x is greater than 75, then the boundary then it's a 6, otherwise it's not a 6. Okay. Yeah, so what professor showed in the video was that he checked, he manually he manually checked it using this time series data, but you can easily use the event function to do the same thing. Okay, I will just show this last example and then we will end this. So I will just create this function. This x only, t comma y. So yeah, so it's a this is also a second order equation. This is also a second order equation. So I will get four first order equations, right? So the first one, dy1 would be y2, and dy2 would be minus upper times y2. Okay, yeah, so this is the air drag term, right? And then dy3, that would be y4, and dy4 is minus 9.81. I will just name kappa. I don't know what professor took. We'll just check. Does anybody remember what was the value of kappa? Okay, I will take some value. See if this works for that value or not. Let us take 0.6. Okay, so this is my function. Now I will create the event function. I will copy this. Okay, so my condition is on this term, right? On y3. Okay, so I just need to check when my y3 crosses 0. And this is similar to the height example. So we are coming from top to bottom. So I will make this -1 and this terminal is 1. Okay. Yeah. So my t0 would be 0 seconds. Tf would be, I will take some long time, 100 seconds. Then options will be set events at the rate, what is the name, events only. Okay. And then I will copy this part. Okay. And I will change this to 6. This is my T0 and this is my TF. Okay. The initial conditions. So the initial condition for x is 0. Also, one more thing, I just need to make this a column vector, otherwise it will give me an error again. Yeah, so the initial condition for x is 0, and the velocity is v 35 cos pi by 4. So I will write that 35 into cos pi by 4. For h is also 0, and the velocity is 35 into sine pi by 4. Okay, fine. And I'm giving options as the event function. Okay. Hopefully this should work. Just run this. Yeah, sorry. This is 6, not 6. Yeah, so it has run, and I can see that my t at 5, the simulation is stopped at 5.046. So that means at 5.046, the h value became 0. So if I check my ye, yeah, so this has become 0, but my x value is still 40 meters only, right? So probably for this kappa value, he will not be able to hit 6. I don't know what value professor took in the video lecture, but okay, let us try for some small kappa value. Yeah, so if I change my kappa value to 0.06, so now my ye value is 100.74. That is my x value. This is my velocity in x direction at that value. This is my y value, and this is my velocity in y direction. So when the ball touches the ground, the x displacement has already reached 107 meters, so probably he will hit the boundary. Okay. What professor showed in the lecture was that he just ran the entire simulation for 100 seconds, and then he manually checked uh, when y3 was 0, what was the value of y1. Okay. So we can do this using this events function also in a much more uh, elegant way, or you can also check for other conditions. Okay. Fine. So I have one more problem to discuss, but the time is already up. I have given you the solution for this. It's in this rabbit fox problem. So you guys can first try to solve this using the event function yourself, and then you can check the solution over here. Fine. So any doubt in any question or any assignment problem? Otherwise, we can wrap it up. Any doubt, Sumit, Anjali?
No, sir, no doubt.
Okay. Okay, then we will end this lecture, and we will meet same time next week. Fine. Good night.
Thank you, sir. Good night, sir.